Hey guys, it's Miss Johnson, and I'm here to bring you the last piece of chapter 2.2. This is a long section. This is the first introduction to normal distribution, and that is a big, huge piece of what we do in this course. So it just takes us a long time to get through this. So thanks for hanging in there with me. So far we've talked about density curves, area of one underneath the curve. Normal distribution, which is a density curve, but it's in that bell shape where you've got the empirical rule of 68% within one standard deviation, 95 within two, 99.7 within three standard deviations of the mean. And then we talked about how to calculate certain probabilities underneath the curve. How do we plug it into our calculator? How do we find a missing score if we know the probability that we want? Today, we're going to talk about how you assess normality. And we will talk about one other plot that we will look at to determine if a curve is normal or not. So assessing normality, not all distributions are normal. We have already talked about right-skewed distributions and left-skewed distributions and bimodal distributions that have two peaks and uniform distributions. None of those distributions are normal. There's only one normal curve, and it's that normal bell-shaped curve that we see. So while experience can suggest whether or not a normal distribution is a reasonable model, in a particular case, it is risky to assume that a distribution is approximately normal without first analyzing the data. Like other times we analyze the data, we start by making the graph. If the data set is skewed, has multiple peaks, or is not bell-shaped, then there's evidence that it is not normal. Okay, so a lot of times it's really obvious to determine whether it's normal or not, but sometimes it's harder to tell, and so then we have to do a little bit more work to determine if it's normal. If we can determine that a data set is normal, then that opens the door to a whole bunch of analysis that is the basis of this whole course. So there's not a lot of analysis that you can do on a skewed distribution or a uniform distribution. You really want to see if you can get that distribution to test normal. Okay, so let's take a look at IQ scores. It says, are IQ scores normally distributed? Many people believe that's supposed to say many, not may. Many people believe that the distribution of IQ scores follow a normal distribution. Is that really the case? To find out, researchers obtained the IQ scores of 60 randomly selected fifth graders from one school. Here are the data and a histogram and summary statistics of the data. So you're asked, is the distribution of the IQ scores of fifth graders at this school approximately normal? Justify your answer based on the graph and the empirical rule. So that's what we're going to do here is we're going to look at this data and we're going to look at the empirical rule and see if we can make this data kind of fit. The nice thing is we have this and we have this, okay? So we can take a look and use that information for us. We also have the original data set, okay? All right, so what we want to do is we want to take the mean and we want to see if we can fit the data within one standard deviation, within two standard deviations, and within three standard deviations of the mean to fit that 68%, 95%, 99.7%. So the first thing that I'm going to do is I'm going to look at the mean plus or minus one standard deviation. So mu plus or minus one standard deviation, okay? And let's see how much data fits into that range. So that means I have that 114.983, and that's plus or minus 1 times the standard deviation of 14.801. Okay, this is going to give me a range, and I should have moved that a little bit down. Sorry, I'm going to come down here a little bit. That's going to give me a range of 100.182 to 129.784. And then the question is, so if that's the range within one or plus or minus one standard deviation in either direction, how many data points fit in that range is what we want to ask. So our data, fortunately for us, our data is listed in order, which is nice. If I look at that range, I'm looking at 100.8 1, so I can't technically include the 100, but I'm going all the way up to 129.7, which means right there. Let's count how many data points that is. So in each row, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that's 22, that's 33. 34, 35, 36, 37, 38, 39, 40, 41. So this is 41 points out of the 60 that we're looking at, and 41 divided by 60 gives me 0.683. Sorry, I'm running out of room here. Okay, so that's a good start. I know that I'm at 68% of the data there. So within one standard deviation in either direction is 68% of the data. Check. Meets the first round of the empirical rule. So let's try the second one down. So now I'm going to do mu plus or minus 2 standard deviations. That's at 114.983 plus or minus 2 times the 14.801. And if I plug that into my calculator, I end up with a range of 85.381 through 144.585. This gives me, so I'm going from 85, so right there, all the way up to 144.58, so everything except that last one. So I did have 41, now I'm at 42, 43, 44, 45, 46, 47, and then 48, 49, 50, 51, 52, 53, 54, 55, 56, 57. So I'm looking at 57 values out of the 60 scores. 57 divided by 60 gives me 0.95 exactly. And then the last one, I want to see that I get about 99.7%. So that's mu plus or minus 3 standard deviations, 114.983 plus or minus 3 standard deviations. And I get a range there of 70.58 through 159.386. So when I do that, I'm looking at the whole set. So I end up getting 60 out of 60, which is 1.0, or in other words, 100%. So it's not exactly the empirical rule. I get 68.3, then 95, then 100%. It's not quite exact. However, it fits so closely that we could say that this distribution is approximately normal. So if I was going to write this up, that's what I would say. I would say that the 60 fifth graders IQ scores follow the empirical rule. Fairly closely. Empirical rule, fairly closely. I'm sorry, I'm running out of room. So we can, I'm going to come up to the top up here, sorry. Say that this distribution is approximately normal. Notice the word approximately. Okay, the word approximately is important. Almost never. We've talked in this class about how we can't ever use extremes. We can't ever say that something is always this way or something is never this way. We don't ever want to talk in those extremes. We are going to use a lot of loose language because you can see that the data is not perfectly normal. That's a clear picture there. And you can also see just by the fact that it doesn't perfectly involve or match the empirical rule, but it's so close that we can say that it's approximately normal. And getting it to be approximately normal is enough for us to be able to move forward and do more analysis. All right, so now let's talk about a normal probability plot. A normal probability plot is another way of looking at a distribution of data and to make sure that the distribution is normal or not. So it says a graph called a normal probability plot provides a good assessment of whether or not a distribution of quantitative data is normal. The normal probability plot is a scatter plot of the ordered pair, which is the value and the z-score. So instead of plotting like an x and a y, you're plotting the value with its z-score, okay? So what we want to see, it says for each of the individuals in the quantitative data set, that is, the x-coordinate of each point is the actual data value, and the y-coordinate is the expected z-score corresponding to the percentile of that data. So there's the scatter plot. It's a data value for your x and then a z-score for your y, so you can kind of picture what it's going to look like. It provides a good estimate of whether or not distribution of quantitative data is normal. If the points lie in a straight line, then the data are approximately normal. That's the key. What you're looking for is points to be approximately in a straight line. Okay? A nonlinear form indicates that it might be non-normal for the distribution. So here's some examples. You can see that we're looking at 4 different examples here of data. So the first one, your data kind of starts here, curves down a little bit, then curves back up. You want it to be that red linear line. When it curves concave up like this, that's a right skewed distribution. It says the plotted points appear to bend up to the left of the normal line. Okay, that indicates that it tails off to the right. When it concaves down like this, that's a left skewed distribution. When it creates like kind of a funky S that comes down, it says short tails. An S-shaped curve indicates shorter than normal tails. So that might be like a really straight up and down, and you have less variance than expected. If it has a funky S that goes up, then you've got long tails. You've got long tails, and your curve would be kind of flat almost, okay? So those are just some probability plots that are not normal. These are all things, I should put my R in there. Not normal, okay? Okay, so we're going to play a little matching game here. We've got 3 normal probability plots and we've got 3 histograms, and we want to look at which one fits with what. So remember that right skewed normal probability plot. So if I look at the first histogram, this is definitely a right skew. The right skew was a The right skew was a concave up normal probability plot. You can see that they also kind of trail off there, and there's a gap. If you imagine, let me erase my markings so you can see a little better. If you imagine these values dropping down to the x-axis, you can see that there's a space right here. That corresponds with that space right there in the plot, and you can see that these two things go together, okay? Another one to look at, if I look at option B, plot B, I can see that I've got a concave down, which suggests that it goes with this left skewed graph, okay? So you can also say, drop these down to the x-axis and see some space right there, and then things get really clumped together up here at the top. And these bars down here on the left of this histogram are really short, meaning there's probably some data spaced out in those intervals. I would take these two and put them together. So then hopefully that means that our last one would fit with the last probability plot. This definitely looks more normal. It does have kind of that weird drop off in the middle, but remember, data is not always perfect. That's why we call it approximately normal. And this looks fairly linear. It's got some space at the end because things do start to trail off, but that's what we expect. We expect to see that your tails trail off a little bit. So I would put those two things together. All right, you can create a normal probability plot on your calculator. These are the calculator steps that you would do to do that. You have to put your data in. That's the first step. So that stat edit menu, and then put your data in. Typically we work in L1 for each data set to start. Then we want to go to the stat plot, which is second y equals. We want to put your stat plot on. And then the last graph option from the graph menu, you're going to enter the information that you know. So you see what list your data is in, and then you can hit zoom 9 and graph it on the plot. And there's a whole tech corner that talks about making probability plots on page 136. This is page 136 in your book. So you can look up page 136 for more information if you would like help with that. Okay, so let's go ahead and calculate a normal probability plot. So the first thing that I'm going to do is I'm going to go into my stat editor, stat edit, and I'm going to clear out list 1. If you don't remember how to clear out your list, you want to arrow up to where the L number is highlighted. So you're going to arrow up to where L1 is highlighted, hit the clear button, and then arrow back down. And then you're going to type in your data. So I'm going to type in 100, 98, 101, 93, 123, 112, 85, 76, 119, and 111. So there's 10 data values there. Okay. I'm going to first create a histogram. So I'm going to go into my second stat plot. I'm going to turn my stat plot on, and I already have a histogram highlighted for that stat plot, and I'm looking at L1. So then I'm going to go to my home menu, and I'm going to hit zoom 9, and zoom 9 is going to give me a histogram. Now the histogram here for me looks kind of funny, but that's okay. Do you know, by the way, that you can hit the trace button? When you hit the trace button, that will tell you what values you're looking at on your X and Y axis. So I know that this is a minimum of 76, and I know that it goes up to 87.5. This is the graph my calculator, or 87.75, sorry, not 87.5. And my bar went up to 2. So that's a 2, we'll call that a 1. Then the next thing is 87.75 to 99.5. And that was also a 2. Now we don't have a very large data set here. This one goes up to 111.25. This is a 3. The next one is back down to a 2. It goes to 123. And then the last one goes up to 134. And it's a 1. Okay, so that's what my calculator did for a histogram. Now, our data set's not very big. Our data set does not have a lot of data in it, so it doesn't give you a lot to base your histogram off of, which makes it kind of hard to tell. But that's my histogram. Now I'm going to go back and I'm going to do a normal probability plot along with it. So if I go up to stat plot and I go into, go back to your plot 1, under type, the very first graph that you see is a scatter plot. You don't want that scatter plot. You want to scroll all the way to the end and you see another plot that looks almost linear, but it's got some scatters on it. You're going to click on that. Your data list is still L1. Your data axis is going to be the x-axis. You want your data to be on X. And then you're going to go zoom, and I'm going to once again do zoom 9. So here's what my normal probability plot looks like. I'm going to draw the same x-axis, and this time my x-axis is in the middle, because remember, some of our z-scores are positive and some of our z-scores are negative. So this is graphing the data versus the z-score. And you can hit the trace button again, and that will tell you where your data points fall. So my furthest away data point, if I say this is my -1, this is your 0, so these are z-scores. I should put this as frequency up here. Okay, so this is 0, here's my +1. My lowest value is here at the 76. I'll change these to purple. Is -1.64. And all I'm doing is hitting the trace key. So now I'm going to trace over. Then when I get to 85, so I'm right about there, 85 is at -1, like almost exactly -1. 93 is going to be at -0.67. Sorry, that rogue purple got in there a little bit. 98 is going to be negative 0.4. 100 right above this is going to be negative 0.1, so just underneath the 0. 101 is just above the 0 at 0.125. Then I jump over to 111, which is over here, and that's up at positive 0.38. So it's up a little bit higher, not quite to a half, but close. 112 right next to that makes a little jump to the 0.67. 119, and again, once again, all I'm doing is hitting the trace feature and tracing across those points. If you arrow left and right, it'll highlight the points and tell you the coordinates. So 119 is at 1.03. And then the last one, 123, is at 1.64. So that's up a little higher. All right, that's my normal probability plot. So this is histogram. This is normal probability plot. Okay, and the x-axes are the same. So if I was going to mark my x-axes, I could mark them about the same as this, but I'm using the same values on this x-axis as I am on that x-axis, okay? If I look at that normal probability plot, I would definitely say that makes a linear pattern, okay? The normal probability plot is linear. So that tells me that the distribution is approximately normal. Approximately normal. Sorry, I always run out of room for my explanations. Okay. So again, that normal probability plot is just one other tool that you can use to assess normality. We also talked about using the empirical rule to assess normality. Both of them are great ways. Both of them are very helpful and applicable. And all of it is just to get your data point to a place, or get your data set to a place where you can call it normal, and then the doors are open for you to do so much more analysis, which is what we're going to talk about basically from about chapter 6 on. If we can prove that things are normal, then we can analyze and do a lot more with it. All right, so that is finally the end of section 2.2. Thank you so much for listening and for joining me for all 3 of these pieces. I know it was a long one to get through, but there's only 2 sections in chapter 2, so that's a good thing. I hope you guys have a great day, and I will catch you next time.